Okay. Good afternoon, everybody, and good morning for our invited speaker. Good afternoon, everybody, and good morning for our invited speaker. Okay, sorry. Continuing with the lectures of the special courses at the National Observatory, I am pleased to introduce the speaker of the next presentation, Dr. Željko Ivezić. Dr. Ivezić got his undergraduate degree in 1990 by the University of Zagreb in his homeland, Croatia. And then he got his PhD in physics by the University of Kentucky in 1995. In 1997, he moved to Princeton University, where he was responsible to produce and develop the Moving Objects Catalog of the Slow and Digital Sky Survey, which represented a breakthrough for our knowledge of the physical properties of the solar system minor bodies. Since 2004, he is professor at the Department of Astronomy of the University of Washington in Seattle, where his research interests include a broad range of subjects from cosmology to solar system objects and the processing of big amounts of astronomical data. Currently, he is the construction project director of the Rubin Observatory Legacy Survey of Space and Time, also known by its initials LSST. He is the author of the code DUSTY for simulating dust radiative transfer, and he has an asteroid with his name awarded by the IAU in 2010. Dr. Ivezić, thank you very much for having accepted our invitation. It is a pleasure to have you today here with us, and you are welcome to start when you are ready.
Thank you so much for this kind introduction, and thank you for inviting me. I wish I could be in Rio with you. Seattle is rainy and dark right now. So my understanding is that the audience is mostly grad students and that I have about 50, 60 minutes for presentation and then about up to half an hour for discussion.
Correct.
Okay. So that's one of the late images of the observatory. So what I want to do today is just to go with a brief, gentle introduction into astronomical surveys. Why are they different from other things we do in astronomy? And what are the drivers for this new survey that we want to undertake once the Rubin Observatory is done? And just to avoid confusion with names, the institution itself, the observatory, the building, that's called Vera Rubin Observatory. Now, what that observatory will do for the first 10 years of its existence is called Legacy Survey of Space and Time. So that's a project, 10-year project that will produce a map of the sky. That's LSST. The institution itself is Rubin Observatory. It may do something else after LSST is done. We don't know yet. So I will first present motivation for that new survey of the sky. And then I'll tell you a little bit about the construction of the observatory. That survey cannot be obtained with any other observatory. For example, if we use Gemini South or Gemini North or VLT or Keck, because they have smaller field of view, it would take 1,000 years, not 10 years. So we needed to build a new observatory, new observing system. And then at the end, I will mention few challenges for data analysis, because this will be a giant data set. Images alone will be 60 petabytes or 60,000 terabytes worth of images. So there will be new challenges for data analysis that we will need to learn how to address. So I'll finish with this, and then hopefully you will be asking questions along those lines and we can have more discussion. So if you are entering the field of astronomy and you ask yourself, how can I be at the cutting edge? Or you can say, well, I actually happen to have $1 billion in my back pocket. Where should I invest it to become cutting edge astronomer? So basically, if you limit yourself in optical, you have three choices. One is to build yourself a very large telescope on the ground, like, for example, European ELT, that will be 40 meters, the largest ever. Or currently, we have 10-meter class telescopes. They are large telescopes on the ground that are probably too large to launch in space yet. Then we do have telescopes in space above the atmosphere. And there are two main reasons why to go above the atmosphere. One is the turbulence in the atmosphere that changes the image quality, the resolution of your images, which is then not limited by the size of your mirror, but it's limited by the properties of the atmosphere. Typically, of the order 1 arc second is the limit that you can do from the ground. A little bit better at professional sites, but roughly speaking, 1 arc second. And the other reason why you would have telescope above the atmosphere is to avoid absorption in certain wavelength ranges that you can only observe from space. Like, for example, mid-infrared or X-rays. You really need to go to space to get efficient observations. And finally, the third way of observing the sky in optical, and it's a relatively new way of doing it, even though it may be the oldest way of doing astronomy, because Hipparchus did first survey thousands of years ago. So recently, with the development of digital technology, with information technology, and as we learn to build ever bigger telescopes for reasonable amount of money, the astronomical surveys became very popular again. And so what do we mean by survey? So when you do classical observation with some large telescope, you basically point that telescope into a given point on the sky because there is some object there, individual object, maybe cluster of galaxies. There is something interesting that you know prior to pointing your telescope at that point in the sky. While with surveys, you basically aim to cover a significant fraction of the sky, or in some cases, the entire sky, without paying attention to individual objects at first. Basically, you want to get image of the sky, and then only later, once you have this data set, you ask specific science questions. You look for subset of objects, you count these objects, you bin them by various properties, you get their distribution relative to each other, etc. So with surveys today, we are able to study billions of objects. So the largest non-digital sky survey was from 15th Palomar Observatory Sky Survey. That was the first modern sky survey done with photographic plates that included hundreds of millions of objects. And since then, we switched to digital technology. So there were many surveys. I'm in particularly fond of Sloan Digital Sky Survey, whose telescope you can see in the upper right. It's a very unusual telescope with this rectangular wind protection, but it was just a cheaper way to do it. And you see the camera, which was cutting-edge camera 20 years ago with its 30 CCDs in 6 columns with 5 bands. So with these surveys today, like Pan-STARRS has over 1 billion objects, Gaia Space Survey has over 1 billion objects, and very soon we'll have tens of billions of objects with Rubin Observatory's LSST. So when you have billions of objects, then you can ask different questions than you could when you only had small samples. You ask different questions and you use different tools and methods to answer them. So here is an example, if you're not optical astronomer, here is an example of a modern digital sky survey. Again, I'm biased towards SDSS, at least until LSST has data. So here is a pretty image, 9 by 13 arc minutes. So slightly smaller than the full moon. And you can see moon at the bottom of slide for scale. So if you look with your naked eye, the typical distance between 2 stars on the sky that you can see is tenths of lunar diameters. So you can see 1 star in about 200 times larger area than what this image is showing. But in this image, there are about 50,000 dots, if you count them with computer, of course. It's a color image. You can see that there are some nearby red stars. There are many yellow and bluish stars. There are not many galaxies because this is looking through the Milky Way disk. There are about 100 to 200 galaxies in this image, so it's dominated by stars. So that's how it looks like. And then you teach computer to recognize each of these objects, and you make what we call catalog, which is basically best fit parameters for various models. Like you fit a Gaussian conceptually, even though you determine point spread function empirically, then you fit that profile to each star to get optimal measurement of brightness, position, etc. And so this development of surveys over the last couple of decades that now led to the third type of astronomer, the survey astronomer. So traditionally we have observers, instrumentalists, and theoreticians. But now we have this new type of astronomer who basically doesn't go to a telescope, but goes to a database or a portal and then downloads data according to some selection criteria and answers some interesting questions. Or as we will have in Rubin, you won't even have to download data. Instead, you will upload your code to our data center, and then you can do science analysis directly without having to shuffle large amounts of data back and forth. So I see my chat popped up. Let me see, is that question? I'm that kind of guy, okay? So I cannot easily see chat, so I didn't emphasize at the beginning. If you have a question, then just start talking. I cannot see you. I cannot easily know that you have a question. So just stop, say question, and I'll stop talking and you ask your question.
Sorry, let's leave the questions for the end of the talk. Better.
We can do that too.
Yeah.
Unless it's something that really prevents you from understanding what's going on, do
Okay.
interrupt me. Longer questions, we can leave for the end. Okay. So with these surveys and other observations, what did we learn so far? So let me just summarize in a couple of slides the main motivation for Rubin Observatory. So we know universe is expanding. This is the gentleman, Edwin Hubble, who discovered it about 100 years ago. And we expected that that expansion will perhaps continue forever, but it will be slowing down a little bit. And that's analogous to if you take a piece of rock and throw vertically above your head. That rock will move away from you, but it will be slowing down and it will stop and then will come back to you. If you throw it really, really fast, faster than speed that you need to overcome Earth's gravity, that rock would then go to infinity. But as it's moving away from you, it would still be slowing down. It would be decelerating, even though it will make it to infinity. And the only way for that piece of rock to accelerate for that stone is to put some little rocket engines on back of it. Otherwise, it has to, as it's losing energy, as it's climbing out of gravitational well, it has to be slowing down. And there was a huge surprise in cosmology about 20 years ago, 25 maybe, when it was discovered that the expansion of the universe is accelerating. So it's expanding ever faster. And that's totally crazy because we don't know what's pushing it. What would be those little rocket engines that you would have on that rock you threw? What is the analogous thing in the universe? We don't know. And so there are two options that we are working with right now. One is that there is something that we call dark energy. It's an extra term in the equation that governs the expansion of the universe that can explain observations, but at the expense of not knowing, not having a clue what it could be. The other option is that general relativity, the theory of gravity, that you assume it's correct when you derive conclusion about dark energy. It could be that that theory is wrong, that there is no dark energy, but instead we need to modify general relativity a little bit in order to fit the observations. And we don't know which one of those two possibilities is less wrong. I'm not going to say correct, but less wrong. And in order to be able to distinguish their predictions, so those two possibilities, they do produce different predictions for the growth of structure in the universe and for its expansion. But how to distinguish them is not possible with existing data sets. And it's relatively straightforward to demonstrate that in order to get statistical power sufficient to distinguish predictions of those two possibilities, you need of the order 10 billion galaxies in your sample. And to detect and measure precisely properties of 10 billion galaxies, you need a new observatory. You cannot do it with existing instrumentation. You need observatory that has sufficiently large telescope mirror of the order 8 meters or more. And even more importantly, you need a very large field of view, much larger than a typical field of view that large telescopes have. In particular, Rubin Observatory will have 10 square degrees field of view, which is about 100 times larger than typical field of view of a large telescope. Now, there is a project called Zwicky Transient Facility, which has very large field of view, even larger than Rubin Observatory field of view, but they have very small telescope. So you need to have combination of both large mirror and large field of view in order to get a survey that will detect 10 billion galaxies to finish in a reasonable amount of time, which we set to 10 years. So here is another way of looking at this problem with galaxies and cosmology. This is cross-section to 3D, that's 2D cross-section that shows positions and colors of galaxies detected in SDSS spectroscopic survey. And the main point of that image is that these galaxies are not randomly distributed in that space, but they form these clumps, and there are voids, there are places without galaxies. And so the statistical details of that distribution encode cosmological information. And so I cannot explain in one slide. There is a whole book by Jim Peebles, Principles of Physical Cosmology, that tells you how do we take now these observations and statistically interpret in order to derive cosmological parameters. So this is what SDSS got, and we want to go further back in past, further out in distance. So that's basically what Rubin Observatory wants to get with LSST. So we want to do similar mapping, but we want to go to about 10 times larger distance limit than we have today. And our sample is estimated to contain about 20 billion galaxies, and about 4 or 5 billion of those will have sufficient signal to noise to do precise cosmological measurements. So that's our main goal in cosmological setting. Now, in the context of Milky Way, we will also push distance limit out because we will have very deep observations across half the sky. We will see further than previous surveys. So in the middle, I don't know, do you see my arrow when I do it on the screen?
Yes.
Excellent. So this little piece, that's real data that goes out to about 10 kiloparsecs. It shows the number count distribution of stars in SDSS. That was a result of about 10, 15 years ago. Then dark energy survey pushed this distance limit to 40 kiloparsecs, although it only had 12% of sky covered, and it didn't have U-band to get metallicity, so it wasn't as good as SDSS in some aspects, but it did push distance limit out to 40 kiloparsecs, discovered many new dwarf galaxies and many other interesting and important results in the context of Milky Way studies. Now with LSST, using the same turn of stars as were used here in this SDSS study, we will go to 100 kiloparsecs, over half the sky. So that will be major push out. There will be few 100 million stars in halo beyond the limit of about 40 kiloparsecs. Before SDSS, there were only about 10 individual stars known at distances beyond 40 kiloparsecs in the Milky Way halo. And now we'll go to hundreds of millions. So our observational material is rapidly changing, and we are learning more and more. And if you took RLIRI from LSST, then you could detect them out to 300 to 400 kiloparsecs, basically to half the distance to the Andromeda galaxy. So we will be learning a lot about intergalactic space too, whether there are individual stars there, etc. And finally, the third very attractive science driver out of many hundreds that Rubin has is this problem of killer asteroids, of hazardous asteroids. So as you may know, there is a mandate to NASA from US Congress to catalog 90% of hazardous asteroids larger than 140 meters. That's roughly the size limit above which you can have huge tsunamis and then you can have impact on people who are living along coastlines in the world, like Rio, and that's where most of population on Earth lives. So it's a very important problem. And at this moment, among ground-based surveys, Rubin Observatory is by far the most capable one, and we believe we'll get very close to fulfilling this mandate. And of course, on top of that, we will also have a sample of about 5 million new asteroids. So today, there are about 1 million known asteroids, and it took astronomers 200 years to discover the first million. And it will take about 3 years to Rubin to discover another 5 million. So it will be big game changer. It will be really transformative for the studies of small objects in solar system. It won't be just asteroids. There will be, of course, lots of NEOs, lots of comets, etc., KBOs. So these are 3 individual specific science cases that I singled out of many hundreds. So basically, we designed this survey, this observatory, by following 4 science themes. So one is cosmology, dark matter, dark energy, etc. One is opening time domain for faint objects. That includes variable stars. There will be few hundred million. Supernovae, there will be few million. And then who knows what we will discover, so-called unknowns. Then solar system structure is one of those 4 themes, which includes main belt asteroids, KBOs, comets, also these dangerous asteroids that I mentioned. And then Milky Way structure with 10 to 20 billion stars, it will also be transformative data set. And we designed this observatory to be powerful enough to address all these science themes with a single data set, essentially. So there will be no time allocation committee that will say cosmology gets, say, 1/4 of the time, solar system gets 1/4 of the time. Instead, we will optimize our scheduler, our robotic brain, if you will, to follow a strategy that will maximize the science that will come out of all of these science themes simultaneously. And so that's the goal of the project. So let me now tell you a little bit about the construction. So to start with the context, these are some of the most exciting new facilities today focused on optical and infrared. So you know, of course, about Hubble Space Telescope, and the successors to Hubble Space Telescope are James Webb and Nancy Grace Roman Space Telescopes. And they go in different directions. They improved on Hubble Space Telescope in 2 different ways. James Webb has a larger mirror. Instead of 2.4 mirror, it has 6.5 mirror, but has very similar field of view. On the other hand, Nancy Grace Roman Space Telescope has almost identical mirror as Hubble, but it has about 100 times larger field of view. And similarly, on the ground, these 3 giant telescopes, ELT, TMT, and GMT, they are trying to push the mirror size by factor of 2, 3, 4 compared to existing facilities. And Rubin, on the other hand, just like Nancy Grace Roman Space Telescope, is trying to push in the direction of much larger field of view. So 8.4 meter mirror in Rubin is a decent mirror, but there are 10 other telescopes, if not more, with the same size of the mirror. However, Rubin field of view is almost 100 times larger than any other of these big telescopes. So that's why Rubin is special. It has the largest ever combination of mirror size and the field of view size. And here you can see Vera Rubin, who the observatory is named after, and she was instrumental in demonstrating that dark matter exists, and by measuring rotation curve of galaxies, she convinced the community that there is something that produces gravity, but we can't see it in photons. As I said, the key trade secret, if you will, of Rubin Observatory, it's the product of 2 large things. Some telescopes like these, ELT, TMT, GMT, they have large mirrors. Some other telescopes, other observatories like Zwicky Transient Facility has large field of view. But it is Rubin that maximizes the product of the 2. And that product is needed if you want to go faint and you want to go over significant fraction of the sky. So that's visualized here. That's Gemini South, our neighbor in Chile. And Gemini South even has slightly larger effective area for primary mirror because we have this giant hole in the middle. It's not really a hole, you'll see on the next slide, but this region that collects photons as primary mirror is larger in Gemini South. However, if you look at the right side, there is huge difference in field of view. About 2 orders of magnitude larger field of view for LSST, for Rubin, than for Gemini. And that's why we can accomplish the 10-year survey about 100 times faster than Gemini could. You'd have to spend 1,000 years to get LSST with Gemini or any other similar 8-meter telescope. And so the trick to large field of view, while maintaining image quality that you need for measuring shapes of galaxies, is design that includes 3 optical elements. So here is primary mirror, this outer part. The blue arrows are photons. So they come from the sky to this outer part. They bounce back to this mirror, secondary mirror, and the camera will sit in the middle here. And then photons go back to the central portion of the mirror, which is different optical figure. This is tertiary mirror. And then it goes through 3 lenses, 3 refractive elements, and then it goes into the camera. And now with these 3 reflecting surfaces, the angles of reflection are different, and you can maintain the image quality. It's called Paul Baker system. Here is the mirror. It was produced in Arizona by spin casting. That's an oven. You can see its edge around. That's the wall of the oven. And it can rotate few times per minute is rotation spin. And you put pieces of glass into it. You put the lid on the oven. You raise the temperature until glass is melted. Once it becomes liquid, then the top surface of that mirror becomes parabola. And it's exactly what you need for optical usage of that mirror. So this way, you save a lot by not needing to polish that parabola out. So once you establish this liquid surface, then you cool the mirror back down so it solidifies. It's a slow process. You have to do it slowly not to get air bubbles and other stuff trapped into the glass. So it takes few months to cool it slowly back down to room temperature. And then this was when we opened the oven and we looked at the mirror for the first time. So to summarize this motivation part, what we want to do is quite simple. We want to scan the sky, essentially entire visible sky above some air mass limit per night, night after night, night after night, every clear night. After about 10 years, it will be of the order 1,000 observations. And then with this map, we will have very faint map when we co-add all the observations. And if you compare each observation to each other, we will have time domain information like light curves, etc. So to those who are not optical astronomers, it is always nice to show the following 2 slides that will show you what is the step forward as we go from SDSS, which is still kind of gold standard in optical astronomy, to LSST depth. So this is now an even smaller image than I showed you before. This is only 3.5 by 3.5 arc minutes. So it's about 1/10 of the full moon across this image. You'd have to have 100 images like this to cover the area of full moon. So it's really tiny on the sky. And so this one goes to 22nd magnitude in SDSS. You can see maybe a few dozen objects. Now, when we go deeper by 5 magnitudes to LSST depth, this is what you see. That's not simulation, that's real data. This is from SDSS. This is from Japanese Subaru telescope, 8-meter telescope, which can go as deep as LSST. The only difference is that they don't have field of view as large as LSST, as Rubin, so they cannot scan the whole sky. But this tiny portion of the sky, 100 of moon's area, they can. And so now you can see as you go 5 magnitudes deeper, you see many more objects on the sky. They're much more redder here because these are larger redshifts. So things change dramatically. And so when you now extrapolate this image to half the sky, it's about 5 million times larger area. So basically what LSST will be is like this image enlarged by 5 million times. So whenever I get tired of Zoom and telecom and work, and I want to get some motivation to survive to the end of construction, I go and flip through these 2 slides. Just amazing. Tells you, gives you taste of what's waiting for us. So what will be LSST? LSST will be an optical near-infrared survey, half the sky in 6 bands, similar to Sloan bands, 27th magnitude, based on about 1,000 images over 10 years. It will be of the order 100 petabytes of imaging data. So it is not easy to handle that and process that. It's corresponding to 1 billion 16 megapixel images, which is like still typical cell phone, as if though you made a picture of billion families in the world. When we will process these images, we estimate that these images will contain about 40 billion objects. About half of them will be stars, and about half of them will be galaxies. So that will be for the first time in history that astronomers will have cataloged more objects than there are living people on Earth. You could literally name a galaxy and a star after each living person on Earth. In the lower left, you can see 8 of projection of equatorial coordinates and the sky coverage. So the green is what we call the main survey, that uniform data set that will enable all that science that I mentioned. And then about 10% of time will be spent on some specialized observations like so-called deep drilling fields, these yellow circles that will have 10 times more observations to see what would happen if we had 10 LSSTs instead of 1. Then there is this north ecliptic spur that is designed to improve completeness for outer solar system objects. And then there is galactic plane and south celestial pole that will have fewer observations because they get to, in galactic plane, we get to confusion limit much faster than at high latitudes. And south celestial pole, we want to close because it will improve stability of calibration, and we don't want to leave holes that we can catch. So that's LSST in 1 slide. The observatory itself will be in Chile. There will be 2 dedicated links for data transfer. One goes through Brazil. That was Brazil's contribution to Rubin Observatory, in addition to other contributions. But that link you see going through Brazil, that is your contribution. Then it will go to US data facility, which is now at SLAC in California. This is a slide that needs update. This August of this year, we turned off the computers at National Center for Supercomputing Applications close to Chicago and switched the processing to lab SLAC next to Stanford University in California. There is also a French site in Lyon that will process half of the data release processing, and there will be site in Edinburgh that will process 1/4 of data release processing. So there is significant participation from UK and France in data processing. Let me show you now a few quick photographs that demonstrate the status of the site. That's me pretending to be useful about 7 years ago. That was the beginning of construction in 2015, where this parking lot is. This is now observatory site. In the background, you can see Gemini South, and far left, you can see SOAR telescope. So the team is many hundreds of people. That was just before the COVID, when we were in Tucson. Then this was during COVID, just on Zoom. And then finally, this summer in August, we met again in Tucson for the first post-COVID in-person meeting. We have about 2 years to go, and then most of these people will switch to operations. Some of them will go to new construction projects. So I have a little video, it's 1.5 minutes, that summarizes nicely what happened over the last 6 or so years of building the observatory. So first we had to level the mountain, 2011, that was done with private funds. Then we started building when we got the big federal grant. You also can see another hill on the right, that's for our calibration telescope. The dome is being built by an Italian company. The telescope was constructed by a Spanish company. Here you can see progress. Sometimes we get snow too. There were many surprises on the site, and things were not going as fast as we thought. Then COVID came, so altogether caused delays, and we still have 2 years to go. Although according to original plan from 2015, we were supposed to be done by now. But I hope next few slides will convince you that these are just delays and that we are on robust path to success about 2 years. You can see how the last piece of telescope was put in the ground. See, there we go. That's how it looks today, or as of a few weeks ago. It's quite impressive to come there and just stand in front of it and see how huge the building is and how beautiful and shiny. So if you will be around CTIO observing or in that part of Chile, I encourage you to come and visit. This is the telescope when it was assembled in a factory in Spain before we disassembled it again into about 10,000 pieces that were shipped to the summit and then reassembled, and it's almost done now. It's already moving under computer control with its own drives, and it's ready for integration of the optical elements. We'll start with surrogate elements in about a month, and then early next year, we are going to integrate real glass, those mirrors that I showed you earlier. It looks like an unusual telescope. It's not very long. It's very squat, very small moment of inertia. And the reason is that we want to be able to rapidly move from one field of view to another in about 5 seconds so that our observing efficiency doesn't suffer from slowing. Here it is, the same instrument, but now reassembled in our dome. And here is the camera. So the camera itself is marvel of technology. It's already in the Guinness Book of Records as the largest astronomical camera ever constructed. So you can see some elements here. This is entrance lens. You can see it here. This is where that lens comes. And as you may remember from your early astronomy classes, the largest telescope refractor is Željko's telescope close to Chicago that has a lens of 1-point-something meters that for almost a century was the largest lens ever produced. Now this one is this is 1.6 meters, the entrance lens for LSST camera. That is the largest lens that was ever produced. That's now also in the Guinness Book of Records. Here is the schematic of the focal plane. So there will be 3.2 gigapixels, 3,200 megapixels in the focal plane. And the way that we got there was modular design. So each of these big red squares on the left is something we call the raft. It has 9 CCDs. Each CCD are these tiny blue squares. You can see rafts on the right when they're taken out. So they contain their entire electronics underneath this 3x3 cell with CCD. So they're essentially replaceable. They're all identical. You can take one out and put spare one in. And so by combination of these 21 rafts, we get to 3.2 megapixels. Each CCD is 16 megapixels. Here is one image, one photo from the process of inserting these rafts. They have very small tolerance. So putting one raft in the focal plane requires a specially designed robotic hand, and it took many hours to insert each of these rafts. Here is the completed focal plane. The camera is essentially operational. It is still at slack, but we are getting images on the test bench to measure, for example, things like readout noise, gain, etc. And it's hard to explain how many pixels is 3.2 gigapixels because your eyes are simply not capable of resolving that many resolution elements. So if you took one image with that camera and you wanted to increase it so that your eyes, the resolution of your eyes, 1 arc minute, it's adjusted to the size of pixels, you would need 1,500 high-definition televisions. So then if you had this image printed on a poster as big as this building, then you could walk along the building and your eyes would have resolution that corresponds to that image. That's how much information is contained in that image. That's why I called my lecture the greatest movie of all time, If you now wanted to look at all the data, all the images with 30 frames per second, like in a TV, it would still take you 11 months to look at all the data that LSST will have collected, adjusted to the resolution of your eyes. And finally, in addition to telescope and the camera, there is the third component of the system, and that is, of course, software. So we need to process a huge data set of 64 petabytes of data, just images without any other metadata. And not only that we need to handle these images, what we want to do is to reduce them, calibrate them so that you have science quality images where the pixel values are actual flux, calibrated flux, not just counts, and that your X and Y positions of these pixels are well calibrated astrometry. And not only that you have images, but we want to teach computers to recognize where the objects are, measure their properties, and produce catalogs that will include close to 40 billion objects. And then each is observed about 1,000 times. So you will have about 40 trillion measurements that you need to handle. And those measurements, then we want to make available to everyone in an easy to use science-ready way through our science portal that we call Rubin Science Platform. So to accomplish all these steps, we need quite exquisite software development. And indeed, we had close to 100 people working for over 10 years on development of the software that we need. So I'll just flash, for those of you who love astronomical software and data processing and pipelines, I'll just flash this diagram without going into details. We have conceptually about 8 fundamental pipelines. And the number one, that's standard processing that, for example, SDSS had. Everything SDSS did is in that number one processing. Now, we have 2 additional sets of pipelines. There are those called yearly data releases, where we co-add many images to go deeper, and then we analyze that multi-epoch data set in new precise ways that didn't exist in SDSS. And then we also have daily processing, where each new image, as it's taken, is subtracted from the previous co-added image in order to see what changed on the sky. So we look for objects in that difference image, and then we either get new data for variable objects like variable stars, or we discover completely new objects like supernovae or gamma ray burst afterglows, or we get detections of moving objects, and then we have an exquisite pipeline that looks at all individual detections of moving objects, tries to literally connect the dots, and then compute orbital parameters so that you can predict in future and in past where those objects were, and then you can distinguish those moving known asteroids from other transients on the optical sky. So this is close to 1 million lines of code, mostly in Python, some of it in C++. So here is illustration of what I just said in words. This is the first step. This is actually SDSS example, where you go with a raw data frame that has a lot of instrumental artifacts. Then you correct for all of them. Then you calibrate it. Then you find objects, those little footprints, those little rectangles in the bottom are individual objects. Then you measure them, meaning you fit some models to it. And then you can reconstruct the entire image. If your models are correct, you describe the entire image with those models and best fit parameters. Now, with image differencing, you now have the following. You have image 1 and image 2. There are 2 examples, top and bottom. You subtract 2 images. If nothing changed in them, then the difference image should be just background noise. And that's exactly what happens in the first row. However, if there is a new object, then when you subtract image 1 minus image 2, you get detection in this difference image. It's black because it's negative. If you subtracted 2 minus 1, then it would be bright. And so in this difference image, we then search for objects and we report them within 60 seconds in alert stream that everybody in the world can access, and then deploy additional instrumentation either to get better time resolution or to get spectra or to get different wavelengths other than optical, etc. So there are different types of follow-up observations. And in 10 years, we will issue of the order 10 billion such alerts. So where do we stand with construction? It's still uncertain at the level of a few months. We are still recovering from COVID impact. We lost at least 2 years due to COVID. So we are still regrouping, so to speak. So these dates are not precise at the week level for sure. They're still uncertain by a few months. But roughly speaking, by next summer, we expect to get engineering first light images with commissioning camera that looks like real camera, but only has 9 CCDs instead of 189. So that hopefully will happen next year. That will demonstrate that telescope is working and that our software framework is working. Then early next year, we'll ship the big camera from SLAC from California to Chile. And then after reassembling it and retesting it, we hope that it will get first big images, 3 gigapixel images in March of 24. And then by the end of 24, we hope to be done with construction and we hope to enter operations. In other words, to enter this steady state observing that is supposed to last 10 years, that is supposed to deliver LSST, Legacy Survey of Space and Time. So it's just around the corner. It's now a good time if you're a grad student to think about doing thesis with LSST commissioning data and early survey data. It's time to start learning about how to handle this giant data set. There are lots of things to learn. And fortunately, we already had data previews that probably some of you even participated in, where you can get account on our Rubin Science platform and you can access the data that looks very similar to what we will be distributing eventually, but it's still based on simulations, on simulated images, but it's excellent for learning how to process the data. So now is the time to start learning if you're interested in becoming a power user of LSST data. So let me conclude by a couple of slides that now are stepping aside a few steps and looking at this problem of data analysis from mathematical point of view, from machine learning point of view. So what we will get from Rubin and LSST. So there will be a database of the order 100 petabytes and a similar size image collection, also close to 100 petabytes. So in this database, in that catalog, you will have data for 40 billion objects. And each of these objects will have about 1,000 measurements, 1,000 epochs. It will be in 1,000 images. When we measure properties of the object, we measure, of course, position, we measure shape, we measure flux, we measure many other numbers, but let's say that we measure just 10. There are many more than 10, but let's say 10. So each of these 1,000 measurements, you measure 10 numbers. So that's 10,000 numbers. So you can think of this catalog as 10,000 dimensional space. And in that space, there are about 40 billion points. So it's highly multidimensional space, and it's highly voluminous data set. And so what do you want to do then with it? Well, basically what you want to do with it is what we are already doing in astronomy. It's characterization of known objects. It's illustrated in that image on the left. It's only 3-dimensional space. It's not 10,000 dimensional space. But if you now think of distribution of objects in that space, there will be some morphological features in that space. You can see donut, you can see something that looks like used bubble gum or a tooth or something. So you want to characterize this morphology. And in 3D, you can plot and see the clustering. 10,000 dimensional space is slightly harder. Then you want to classify these morphological things. You want to match with additional data sets that will tell you, for example, that one of these is stars, the other one is galaxies, the third one is variable stars, et cetera, et cetera. And finally, once you kind of understand the bulk of your catalog, then you want to look for peculiar things, things that are unlike the majority of other entries, which could be problems in your measurements, or it could be extremely interesting astrophysical objects. And usually we know from history of astronomy that often we learn the most when we find very, very unusual, very peculiar objects. So that's what you want to do. We already are doing that today, except it will be a bit harder to do that in highly multidimensional space with billions and tens of billions of objects. So we need to find a way of first defining what we want to do, perhaps reduce dimensionality of this space, perhaps reduce the sample size by focusing on particular type of objects, and then go from there. So another way of looking at the problem is, if, for example, statisticians ask you, why is it hard to do what you do? Then this is my top list of why it is hard to do data analysis with data sets like Rubin will deliver in the form of LSST. So first you have large data volume, you have petabytes. You can't just do that on your laptop. You have to think about how to approach such a large data volume. Then you have large numbers of objects, billions literally. So you can't use Microsoft spreadsheet, Excel or something like this. You have to do some special purpose code to handle billions of objects. Then you have highly multidimensional spaces. And that's important because when you go to scikit-learn or any other machine learning library, many of the methods that are implemented there, they scale with like square of the dimension, or if you're lucky, maybe with d log d, or with size, sample size, it can be n cube. If you're lucky, it will be n log n. So many of the methods that work fine in 10 or 100 dimensions, they just choke when you go to thousands. And then you have to find a way how to solve the problem without relying on existing code that chokes. And that's also a very interesting set of problems. Then often, if you want to do statistical analysis, you need to know what distribution you are working with. And very often in discovery science like astronomy, we don't know that. Then we have time series data for billions of objects. And that will be non-trivial too, because if you look at literature for time series data, which comes mostly from engineering, 99% of those books assume regular sampling because that's what happens in engineering. But in astronomy, we don't have that luxury. And so we need to develop new methods for time series analysis that do not assume regular sampling and that also don't assume homoscedastic errors that are all the same. In astronomy, we have heteroscedastic errors that are different for each object because our objects have different brightness. And that means we get different number of photons from them. And because our random noise is dominated, at least at the faint end, by the number of photons, then each object has different uncertainty. And sometimes data are truncated, sometimes they are censored. So sometimes object is fainter than your faint limit. Sometimes it falls in the gap between the chips. So you need to account for all these effects. That's why statistics in astronomy is probably the hardest than in any other field. And so there is more to this discussion. I give you this link to Astro PH paper where a couple of colleagues and I thought about what will be hard things to do in the era of LSST. And finally, since you're grad students, I want to mention a book to you where some main methodology and methods of analysis that we will need are covered. And so here I have bulleted list of questions I give to my students when they come to exam. Like, tell me, what do you know about maximum likelihood method? Or what do you know about the goodness of fit and model selection? And then I let them go. So if any of these, you cannot stand up and give me 5-minute speech about it, that means you need to study more. And one possibility is to go with this book, or you can also find everything on the web. But these are some of the important concepts you need to know if you want to be power user of LSST data and big data analyst. And so finally, just an illustration of new methodologies that we need. We will need to learn how to efficiently classify images, billions of images. Here is an example that is more appropriate for finding alerts and classifying alerts. So the question is, which of these sheep is different from others? And so obviously one has blue sweater, but that's easy, that you would call it different population of sheep that like sweaters, but you're looking for tiny differences. And so like, for example, this sheep is different from the others because others are mostly sleeping and this ship has one eye open and peeking at you. So now you want to teach computer to do that on much more complicated images than this ship, and not just on a handful of images, but on billions of images. So that's another interesting problem we need to solve. So let me stop here. It's about an hour since I started talking. So in summary, LSST will come soon. It will take 10 years to collect those data. We will be starting science right away, of course. But after 10 years of surveying, we will have the largest ever catalog of astronomical objects that will be tens of billions of objects, 20 billion galaxies, 20 billion stars, 10 billion alerts. And then, as Carl Sagan would say, millions and millions. He said billions and billions of galaxies. Here we have millions and millions of supernovae, of quasars, of asteroids. There will be fantastic new science that we will be able to do. And a lot of processing of this data will be already done for you by Rubin Observatory and made available through Rubin Science platform. But one message I want you to remember, since you're in grad school, is that how many papers will be published, either we as community or you personally, will be bottlenecked by software that you will have at your disposal to use, either from somewhere else or developed by you if it's special purpose code. And so, unlike traditional astronomy, where you could get away without knowing much software like 20, 30 years ago, today, if you want to be at the cutting edge, at the very least, you'll have to learn tools that we will provide to you through Rubin Science platform. And in special cases, you will develop your own software, your own tools to extract science and to be competitive in this context. So I will stop screen sharing here. And I'm now open for your questions.
Okay, thank you very much, Željko. It was a wonderful talk. If you want to make some questions, please raise your hand and open your microphone. Simone, go ahead.
Yes. Okay. So thank you. It was really impressive. It's really impressive project. Large amount of data, a huge challenge to handle all this data. And as you said, it's a new a new way of doing science. So it's really a challenge for everybody, especially for the new generations of astronomy or astronomers to come. And I have a question regarding these alerts. What's the threshold to trigger such an alert of a new object? What's the minimum difference in magnitude? Because of course, many objects will present some variation, but what's the minimum difference that will trigger an alert?
Yeah, understood. So the alerts will be defined not by difference in magnitude, but by signal to noise ratio in different images. So you subtract the two images, and then there will be objects there. If one star, for example, became brighter by 0.1 magnitude, 10% brighter, then that star will have certain signal to noise ratio with that change in difference image. If that was very bright star, where you can measure the brightness with 1% precision, then 10% change will be 10 sigma, 10 signal to noise ratio of 10. It will be detected. But if a faint star changed the magnitude by 0.1 magnitude, its brightness by 10%, but that faint star is at the limit of detection where it has errors of 0.2 magnitude, then 0.1 magnitude is only half a sigma deviation. So that star would not be detected in difference image. That at its brightness, that brightness change doesn't give you enough signal to noise ratio. So detection is basically defined just like in static images. You go down to some signal to noise ratio, and then you report everything above that ratio. Now, eventually, if you will have variable star or any other transient object, and you want to know whether it was detected before the first LSST detection at 5 sigma, you will be able to access those images and that position, and then do what we call forced photometry. You just put point spread function down there, you measure the flux, and so if that flux is 3 sigma detection or 2 sigma detection, you will know it. Now that you already know the object exists. First time, it has to be 5 sigma to make it into our stream. Does that answer your question?
Yes, sure. I have a second question. You mentioned that you can one can upload a code and then run the code with the LSST data. But and when you upload this code, so this makes your code like available for all the other users, like some kind of GitHub.
No, if you want to. So if you want to share it, you can. You don't have to. And the same applies for the results of your code. For some, say, catalog or measurements you make, you can make it available to others, or you can keep it private to yourself. And then there will be something similar to time allocation committee, but it will be allocating computer resources. So each user who registers will have some amount of compute power, some amount of disk, like a sandbox to play with. So let's say you can take 1% of data and you run for 10 hours and you demonstrate your code on some galaxies, calculates something useful. Now you say, I demonstrated it works, but now I need to run it on 100 times larger data set. So now my preliminary allocation I got as every other user is not sufficient. I need to apply for more time. And then there will be competitive time allocation committee, and then you will be able to get more time.
Okay, thank you.
Carvano, please.
Hi.
Hi.
Thanks, Željko, for this very nice talk. I'm wondering about asteroids. Of course, you have a lot of asteroids discovered, you have a lot of photometry for asteroids. But about asteroid colors, what can LSST do about asteroid colors?
So as you imply, it will not be simultaneous multicolor photometry like in SDSS. So there will be sometimes few days apart between the observations. And because of rotation, we know that there will be amplitudes in each band, even one magnitude amplitude. So you can't simply just connect them. You need to do some intelligent interpolation. Now, we also know that colors do not vary as much as magnitudes. We know from SDSS that RMS is maybe 0.02 magnitudes or so, much smaller than amplitude of variability in a given band. And so that now gives you enough of information to try to fit some models simultaneously in all bands. We don't have that code yet, but we did apply it to variable stars. There is a periodogram search that simultaneously uses all the LSST observations that are not coeval in the context of periodic variables, and we showed it works on IR Lyrae and other periodic variable stars. Something similar to that can be developed for asteroids too. Whether it will be based on some Gaussian processes plus periodic kernel or something like that, I'm not sure. I haven't seen implementation yet. But bits and pieces exist that indicate that some direction like this will be useful in this context of getting colors of asteroids. There is, of course, then also you have to include slightly more complicated than variable stars, because with asteroids, you need to account for different distance between you and the sun. There are phase effects, so there are more terms in the model. But that is very interesting problem to solve that people are aware of in solar system science collaboration. But as far as I know, nobody is yet working on it. And if you're interested, I would check with the chairs of science collaboration to verify that still nobody's working on it, and then go and solve the problem and become rich and famous.
All right, thanks. I'll think about that. Thank you.
Okay, Julio, please.
Hello, thanks for the excellent talk. My question is about, can you hear me?
Yes, I
Yes.
can. Uh-huh.
Okay, great. Okay, my question is about access to public data. My previous understanding was that if you are a non-LSST member, and if you want to access public data, you should either associate yourself to a data access center, or perhaps to a broker, if you just want transient objects. Is this correct, or something has changed?
If you only want alerts, you don't have to have data rights. Alerts will be available to everyone in the world within 60 seconds. And there are 7 or 6, I forget now, brokers that were declared as official LSST brokers, where we will be sending the full stream of alerts. And then they will allow you to filter that stream and then access those alerts somehow. And those brokers are all committed to be open for everyone.
Okay.
They may be perhaps choked by the number of people trying to access the data. I don't know about that. We'll see in practice how it works. But that's the menu for getting alerts. Now, if you want more data, like for example, in each alert, it will have information, what are the distances to 3 nearest stars and 3 nearest galaxies, so that you have some contextual information. But measurements of those galaxies and stars, like how bright they are or colors, will not be in alert. It would be too much information sending. So you need to have access to static catalogs too, to know what you're working with. And to get to static catalogs, to get to our data releases, you do need to have data rights. And so data rights can be obtained through those in-kind international contributions. And Brazil is certainly contributing. And the model is that every contributor will get certain number of so-called principal investigator slots, PIs, which are senior people. And each of those carries 4 more people who are junior, like grad students or young postdocs, who also get access to data. And so if you're on this list, then you will get your account on our Rubin Science platform. And once you have account on Rubin Science platform, then there is no difference in practice between you and anyone else in US or in Chile, which is host country. So everyone in Chile and everyone in US gets data rights, irrespective of where they are. For other countries, you have to go through this in-kind contribution, and then you get access to our data center. Now, after 2 years, there is no more proprietary period, and everybody in the world can get all the data. However, caveat is that at least the US data center is sized for the needs of US plus in-kind contribution communities. And if the whole world now wants to use the data, they need to think of another way of accessing the data. So we think that there will be other mirror copies of the data around. To begin with, there will be one in UK, there will be one in France, there will be one in US, probably one in Chile. We think that this will now spread to many more places as people start learning the value of the data set. But at this moment, I can't tell you exactly how would you from Brazil, if you are not on the list of in-kind contributions, how would you access the data after those 2 years?
Okay, thanks.
Andres.
Hi. Thanks a lot for your nice talk. I just want to bring back the comment of Simon's comment. So let's say I mean, this data center that you're talking about is like we will have, well, researchers will have access to create, let's say, its own pipelines or codes using like cloud computer or resources from the collaboration. And yeah, that's like one thing that I don't know if I'm explaining myself well.
So you will have access, if you have data rights and you get account to Rubin Science Platform, you will have access to 10% of compute power that we sized for our data processing center. And that's a lot. Now, one can imagine cases where that would not be enough. But because our Rubin Science Platform will run in the cloud, it is likely that you will also have option, and I say it's likely and not it's certain because we have technical capabilities to enable it, but there are some political issues like equity, etc., that we need to resolve. But at least in principle, you could bring additional funds. Let's say Brazilian Science Foundation gives you $100,000 and you can buy cycles from the cloud provider and run whatever you want. You don't even have to go through time allocation committee. You just say, I want to run something on it. I got money. You go to platform and you access the data and then pay extra for cycles directly to the cloud provider, just like we would.
Okay, and I suppose there will be like special standard resources, right? And if, for instance, if someone wants to train like a special machine learning model or heavy computational model that will need some special package that is not in the standard configuration, is it possible to that researchers configure its own environment?
Yes, absolutely. Yeah. You can already do that. Those data previews that I mentioned, they are a great way to try these ideas and to try implementing things so that you are ready when real data come in, you already know how to do it and how to deploy.
Okay, thank you so much.
Okay, Renato, please.
Yes, okay, hi. That's a great talk, very, very nice, very interesting. And actually, I think they already answered some of my questions about, for example, the public data, if I understood correctly, 2 years goes to the public, and then depending on how difficult it's going to be to access, those situations that we don't know yet, right, how it's going to be. But I was wondering about two things. It may be a little too early. Can you say something about the initial survey strategy? Like Carvana mentioned, the cadence for asteroids in different filters might be a very, very tricky situation. But for example, for supernova may not be that complicated. So I was wondering what the cadence is planned, if any, has been defined yet. And my second question was that if there are is there open for instrument development to be put in the LSST before the 10-year period of the survey?
So first, the cadence. So we do have ongoing process of finalizing the initial survey strategy. There is a committee we call Survey Cadence Optimization Committee that already issued one recommendation to operations a year ago. And they're just about to issue second recommendation that now goes to another level of detail. That will be done by the end of this calendar year. And then there will be a couple of still open questions that they will address during next calendar year that are supposed to pay special attention to early science during first year. So they will try to further optimize just the first year of the survey. They will also pay attention to how quickly you can build templates for image differencing. And then there are some open questions about so-called rolling cadence strategy, where you, instead of doing homogeneous coverage of the sky, you focus on a smaller part of the sky, but then you get more data points during that period. So that's good for cosmological supernovae, etc. So there is an ongoing process. If you Google LSST, SCOC, you will get website with all the documents, with all the reports, with the summary of everything that happened so far, with many documents that discuss these gory technical details. So bottom line is there is ongoing process. Baseline looks similar to how it looked 5 years ago, but they are at the 10% level. There are changes that are enhancing science and that are making it better. Now for cadence and then instrumentation. So the question is similar to a broader question of what happens after LSST, after 10 years. And there is a nice Astro PH paper where we covered possibilities. And basically, one possibility is to say, well, this is so good LSST data that we should just get 2 or 3 or 4 more years of it. That's the simplest scenario. The other scenario is, okay, this is good, but let's try to get different filters, like maybe like S+. Let's get some narrow band filters or something like this. That would be easy to implement too in the existing camera. Then you can say, well, the camera was great 15 years ago, but now we have different instruments. Let's do different instrument. Maybe spectroscopic instrument, maybe something else. Who knows? Polarimetry, who knows? So that's another possibility. And so what will happen is unclear at this moment. I think probably after 3-4 years of surveying, when we establish that we are in steady state, people will start thinking hard about what to do next. And then one possibility, if you want to put some other instrument on there, what you mentioned cannot be ruled out at this time. At this time, we do plan, we'll just go for 10 years with the existing camera. But if there was technical or other reason why to take 1 month away from observing with the big camera and then put some other instrument for a test, some pilot prototype that you will later develop into next generation instrument, that sounds to me like a plausible scenario.
Okay. Okay, thank you.
We certainly can take LSST cam, the big camera, off the telescope, and we'll be doing it at least few times in survey. And the camera is designed to be easily taken out. If you need to replace raft, it needs to go to clean room. So technically, it's definitely doable. It will cost you in observing time. So it will be trade-off. Why would we now sacrifice 2 months of observing time to take the big camera off, put another instrument on, do something with it? So it will be trade-off, but it's doable technically.
Good.
Okay, thank you, Renato. I have maybe a last question. You mentioned that those other data centers that will be in the UK and I think in France also, they will host only part of the data, not the whole data. And
no, they will process part of the data, but they will then copy the rest of the process data from other centers. So every center will have all the products.
Okay, but they will have the raw products. If you want to make processing over there, you will be able to process only a part. Oh.
Correct. So they will keep the entire data set for the safety and other reasons. And then there will be software that will say, you guys, you process this quarter, you process this quarter, and you process that half. With some overlap to make sure that they get the same results, etc. But they will be spinning long storage copies of data at all places.
And just a curiosity, what will be the velocity of transmission of the data between the data center in the US and these other data centers?
Yeah, I don't know.
It will be done instantaneously, or it will be done periodically?
I think it will be done on daily basis. I don't know exact measurements for US to UK or France, but I would expect that it's a similar speed as Chile to US. And what I know from measurements is that it takes about 1 second to transfer the image from Chile to US. And that image is 6 gigabytes, 6.4 gigabytes. It's transferred in about 1 second.
Okay. Okay, I think that there are no other questions. We thank again Željko for the talk. It was really wonderful.
Thank you for inviting me.
I have to say that I am a bit depressed after that, because I realized that it is a really very huge task to deal with this data. It's an enormous amount of work that it is necessary to do. We hope it can be at our hand to do that.
On the bright side, we are still young and full of energy, Fernando.
Of course, of course. Well, thank you very much for having accepted the invitation. It was a pleasure.
Thank you for having me, and all the best.
All the best
Thank
for
you
you.
very much.
Take care.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.